Alright, welcome to day 6 of learning OpenGL. Today's topic is going to be coordinate systems. We are almost at the end of the getting started section, so really excited about that. Alright, let's just dive right into it. In the last chapter, we learned how we can use matrices to our advantage by transforming all vertices with transformation matrices. OpenGL expects all the vertices that we want to become visible to be in normalized device coordinates after each vertex shader run. That is, the x, y, and z coordinates of each vertex should be between -1 and 1. Coordinates outside this range will not be visible. What we usually do is specify the coordinates in a range or space we determine ourselves, and in the vertex shader transform these coordinates to normalized device coordinates (NDC). These NDC are then given to the rasterizer to transform them to 2D coordinates / pixels on your screen. Okay. So we need to convert to this NDC, which is normalized device coordinates, which ranges between -1 and 1. And anything outside of this range will actually not be rendered on the screen. And here it says that we determine ourselves and in the vertex shader, and that's where we normalize this. Transforming coordinates to NDC is usually accomplished in a step-by-step fashion where we transform an object's vertices to several coordinate systems before finally transforming them to NDC. The advantage of transforming them to several intermediate coordinate systems is that some operations or calculations are easier in certain coordinate systems, as will soon become apparent. There are a total of 5 different coordinate systems that are of importance to us. The local space, also known as the object space. We have the world space, the view space, also known as the eye space, the clip space, and finally the screen space. So those are the 5 main coordinate systems. Those are all a different state at which our vertices will be transformed in before finally ending up as fragments. You're probably quite confused by now by what a space or coordinate system actually is, so we'll explain them in a more high-level fashion, but first by showing the total picture and what each specific space represents. The global picture, to transform the coordinates from one space to the next coordinate space, we'll use several transformation matrices, of which the most important are the model view and projection matrix. Our vertex coordinates first start in the local space as local coordinates and are then further processed to world coordinates, view coordinates, clip coordinates, and eventually end up as screen coordinates. The following image displays the process and shows what each transformation does. So that means we're going to start with local space, and then to convert it into world space, we're going to use the model matrix. Then to convert it from world space to view space, we're going to use the view matrix. Then from view to clip space, we're going to use the projection matrix. And finally, we're going to do the viewport transform, and that will turn it into screen space. Local coordinates are the coordinates of your object relative to its local origin. They're the coordinates your object begins in. The next step is to transform the local coordinates to world space coordinates, which are coordinates in respect of a larger world. These coordinates are relative to some global origin of the world, together with many other objects also placed relative to this world's origin. Next, we transform the world coordinates to view space coordinates in such a way that each coordinate is as seen from the camera or viewer's point of view. Okay, so that's how we implement the camera, I suppose, by converting the world coordinates into view space coordinates. After the coordinates are in view space, we want to project them to clip coordinates. Clip coordinates are processed to the -1 and 1 range and determine which vertices will end up on the screen. Projection to clip space coordinates and add perspective if using perspective projection. Okay, and lastly, we transform the clip coordinates to screen coordinates in a process we call a viewport transform. That transforms the coordinates from -1 and 1 to the coordinate range defined by GL viewport. The resulting coordinates are then sent to the rasterizer to turn them into fragments. You probably got a slight idea of what each individual space is used for. The reason we're transforming our vertices into all these different spaces is so some operations make sense. All right. It also says that we can actually define a transformation matrix that goes directly from local space to ellipse space, but that gives us less flexibility. Okay, it's gonna define each one of these. This doesn't seem too code heavy. Till we get here. Okay, yeah, it's not too code heavy, but we just need to do these transformations from one space to another. Alright, so local space is the coordinate space that is local to your object, that is where your object begins. Imagine that you create your cube in a modeling software like Blender. The origin of your cube is probably 0, 0, 0, even though your cube may end up at a different location in your final application. Probably all the models you created all have 0, 0, 0 as their initial position. All the vertices of your model are therefore in local space. They're all local to your object. The vertices of the container we've been using were specified as coordinates between -5 and 5 with 0.0 as its origin. These are local coordinates. Okay, so because by default we're using local space, the vertices that we did define for our container, it was actually in local coordinates, and then we can actually convert it into other coordinate systems. If we would import all our objects directly into the application, they would probably all be somewhere positioned inside each other at the world's origin of 0, 0, 0, which is not what we want. We want to define a position for each object to position them inside a larger world. The coordinates in world space are exactly what they sound like. The coordinates of all your vertices are relative to a game world. This is the coordinate space where you want your objects transformed to such a way that they're all scattered around the place, preferably in a realistic fashion. The coordinates of your object are transformed from local to world space. This is accomplished with the model matrix. The model matrix is a transformation matrix that translates, scales, and/or rotates your object to place it in the world at a location orientation they belong to. Think of it as transforming a house by scaling it down. It was a bit too large in local space. Okay, then it's just giving the example. And then we have the view space. The view space is what people usually refer to as the camera of OpenGL. It is sometimes also known as camera space or eye space. The view space is the result of transforming your world space coordinates to coordinates that are in front of the user's view. The view space is thus the space as seen from the camera's point of view. This is usually accomplished with a combination of translations and rotations to translate or rotate the scene so that certain items are transformed to the front of the camera. These combined transformations are generally stored inside a view matrix. It transforms world coordinates to view space. In the next chapter, we'll extensively discuss how to create such matrix to simulate a camera. Okay, so using this view space is actually how you implement the camera. And I guess the next section, which is about the camera, is gonna mainly focus on this thing. The clip space at the end of each vertex shader run, OpenGL expects the coordinates to be within a specific range, and any coordinate that falls outside the range is clipped. Coordinates that are clipped are discarded, so the remaining coordinates will end up as fragments visible on your screen. This is where clip space gets its name from. This is also where clip space gets its name from, because specifying all the visible coordinates to be within the range -1 and 1 isn't really intuitive. We specify our own coordinate set to work in and convert those back to NDC as OpenGL expects them. To transform vertex coordinates from view to clip space, we define a so-called projection matrix. Okay, that's the third main matrix that specifies a range of coordinates, for example, -1000 to 1000. In each dimension, the projection matrix then transforms coordinates within this specified range to normalize device coordinates -1 and 1. All coordinates outside this range will now be mapped between -1 and 1. All coordinates outside this range will not be mapped and therefore be clipped. With this range, we specified in the projection matrix a coordinate of 1250 by 500 and 750 would not be visible since the x-coordinate is out of the range and thus gets converted to a coordinate higher than 1.0 in NDC and is therefore clipped. Okay, so we define our own dimensions, our own range, and then this gets mapped to this range -1 and 1, and say we are here defining a coordinate that's outside this our original range. So when this gets converted, it will actually fall outside this -1 and 1 range, so this coordinate will actually get clipped. Now that if only a part of the primitive, for example, a triangle is outside the clipping volume, OpenGL will reconstruct the triangle as one or more triangles to fit inside the clipping range. A projection matrix creates this viewing box a projection matrix creates is called a frustum, and each coordinate that ends up inside this frustum will end up on the user's screen. The total process to convert coordinates within a specified range to NDC that can easily be mapped to 2D view space coordinates is called projection. Since the projection matrix projects 3D coordinates to the easy to map to 2D normalized device coordinates. Once all the vertices are transformed to clip space, a final operation called perspective division is performed, where we divide the x, y, and z components of the position vectors by the vector's homogeneous w component. Okay, so this is where the w component plays its part in adding the perspective. Perspective division is what transforms the 4D clip space coordinates to 3D normalized device coordinates. This step is performed automatically at the end of the vertex. So we don't need to do this manually. This is performed automatically. It is after this stage where the resulting coordinates are mapped to screen coordinates using the settings of GL viewport and turned into fragments. The projection matrix to transform view coordinates to clip coordinates usually takes two different forms, where each form defines its own unique frustum. We can either create an orthographic projection matrix or a perspective projection matrix. Okay, here it defines what the orthographic is. It has a far plane and a near plane. It's like the frustum is looks like a cube or a cuboid, and any vertex that falls out of this box is clipped. To create this frustum, we need to define the width and height of this plane, and then the length of the visible frustum. So that will be the distance between the near plane and the far plane. The frustum defines the visible coordinates. It's specified by the width, height, and the far plane. Here it shows in code if you want to do this. To create an orthographic projection matrix, we make use of the GLM's built-in function, GLM ortho. Okay, it has 1, 2, 3, 4, 5, 6 parameters. The first two are the left and right coordinates of the frustum, and the third and fourth are the parameters specified by the bottom and the top part of the frustum. Okay. So these first four define the width and height of this plane, and then finally the last two are, I guess, the near and the far plane, the distance between the near and the far plane. This specific projection matrix transforms all coordinates between these x, y, z range values to normalized device coordinates. An orthographic projection matrix directly maps coordinates to the 2D plane that is your screen. But in reality, a direct projection produces unrealistic results, since the projection doesn't take perspective into account. This orthographic projection does not take perspective into account. For that, we use the perspective projection matrix. And then I guess it's talking about perspective in real life. As you can see, due to perspective, the lines seem to coincide, and that's what we try to mimic using the perspective projection matrix. Here what we do is manipulates the W component of each vertex coordinate in such a way that the further away a vertex is from the viewer, the higher the W component will be. Okay, so here we're going to divide the components by W. So the further it is, the larger this W component will be. That means this result will be a smaller number, and that's why it will appear to be smaller on the screen. Each component of the vertex coordinate is divided by its W component, giving smaller vertex coordinates the further away a projection is from the viewer. Okay, yeah, that makes sense. All right, if we want to go into more detail, we can look at this article. I don't think we're gonna have time for that. Okay, yeah, this goes into much more detail. Let's move on. GLM mat4 proj. Okay, so we have a built-in function for this as well, the GLM perspective. What do we do? We give it the angle. I guess that is like the FOV of this frustum. We do the width divided by height, which would give it the aspect ratio, and then this I think would be the near and the far plane again. A perspective frustum can be visualized as a non-uniform shaped box from where each coordinate inside the box will be mapped to a point in clip space. An image of a perspective frustum is seen here. Okay, so it actually looks like a cone, but it starts from the near plane and ends at the far plane. So it's like a slice of the cone, I guess, like a pyramid. Okay, so anything outside this frustum will be discarded. So this angle is what defines the FOV. Its first parameter defines the FOV value. So the larger it is, the broader the FOV will be. For a realistic view, it is usually set to 45 degrees, but for more Doom style results, you can set it to a higher value. The second parameter sets the aspect ratio. It's calculated by dividing the viewport's width and its height. The third and fourth parameters set the near and the far plane of the frustum. We usually set the near distance to 0.1 and set the far distance to 100. All the vertices between the near and the far plane and inside the frustum will be rendered. All right, so far so good. Whenever the near value of your perspective matrix is set too high, like 10, OpenGL will clip all coordinates close to the camera between 0 and 10, which can give a visual result that may have seen before in video games where you can see through the certain objects when moving uncomfortably close to them. When using orthographic projection, each of the vertex coordinates are directly mapped to clip space without any fancy perspective division. Okay, so how this orthographic is achieved is actually you just skip this perspective division that we do, and that doesn't scale the vertices as they go far away from the viewer. It still does perspective division, but the W component is not manipulated. It stays at 1. Okay, so because the perspective division is automatic, I suppose here it says that it's automatic. So what you do is you don't touch the W component, it just stays at 1, so that division doesn't really do anything and thus has no effect. Because the orthographic projection doesn't use perspective projection, objects farther away do not seem smaller, which produces a weird visual output. For this reason, the orthographic projection is mainly used for 2D renderings and for some architectural or engineering applications where we'd rather not have vertices distorted by perspective. Applications like Blender that are used for 3D modeling sometimes use orthographic projection for modeling because it more accurately depicts each object's dimensions. Below is the comparison. Okay, putting it all together, we create a transformation matrix for each of the aforementioned steps: model, view, and projection. A vertex coordinate is then transformed to clip coordinates as follows. Okay, v clip is equal to the matrix projection, the view matrix, and the model matrix, and this is the vertex position in the local coordinate. Okay, so when all of this is multiplied, you get the new coordinates which are in clip space. I think the last one is clip space. Okay, now it's in screen space. Alright, note that the order of multiplication is reversed. Remember that we need to read matrix multiplication from right to left. Yeah, so it goes from model to view to projection. The resulting vertex should then be assigned to GL position in the vertex shader, and the OpenGL will then automatically perform perspective division and clipping. Yeah, so this perspective division is automatic and clipping is also automatic. And then the output of the vertex shader requires the coordinates to be in clip space, which is what we just did with the transformation matrices. OpenGL then performs perspective division on the clip space coordinates to transform them to normalized device coordinates. OpenGL then uses the parameter from GL viewport to map the normalized device coordinates to screen coordinates, where each coordinate corresponds to a point on your screen. In our case, it's 800 by 600. This process is called viewport transform. So I guess that is this step, the viewport transform. So this part, it happens automatically. We just need to do this and get it to clip space and then pass it on to the vertex shader. Then this part happens automatically, the perspective divide, the clipping, and converting it into the NBC. Alright, this is a difficult topic to understand, so if you're not exactly sure what each space is used for, you don't have to worry. Below you'll see how we can actually put these coordinate spaces to good use, and enough examples will follow in the upcoming chapters. Going 3D. Now that we know how to transform 3D coordinates to 2D coordinates, we can start rendering real 3D objects instead of the lame 2D plane we've been showing so far. To start drawing in 3D, we'll first create a model matrix. The model matrix consists of translation, scaling, and/or rotations we'd like to apply to transform all objects vertices to the global world space. Let's perform our plane. Let's transform our plane a bit by rotating it on the x-axis so it looks like it's laying on the floor. The model matrix then looks like this. Alright, so we create a matrix called a model using glmat4. Okay, so this is a what is it called, unit matrix. Okay, it has one on the diagonals. Okay, and then model is equal to glm rotate model glm radians. Okay, it's giving it the angle and then the axis that it needs to rotate on, so it's going to rotate on the x-axis. By multiplying the vertex coordinates with this model matrix, we're transforming the vertex coordinates to world coordinates. Our plane is slightly on the floor, thus represents the plane in the global world. Next, we need to create a view matrix. We want to move slightly backwards in the scene so the object becomes visible. Okay, I'm going to try to do this before moving on. I don't know if all the code is at the end or not. Okay, the model. Okay, just showing the model matrix here. Okay, this is the projection and the view is here. Okay, let's try doing this. So where are we? Okay, I need to clean this up a little bit. This is our second texture. I'm gonna get rid of that. We're also drawing this. Okay, that is the smiley face. We did that. We have these two draw elements, so I don't need the second draw element. This should probably, yeah, now we only have one plane. So here we are actually using the second transformation. We don't need this either, I guess. Yep. Okay. Does it still keep the face thing? Okay, it still has that. So where do I do this model matrix stuff? The shader. This is the texturing stuff. I suppose I can do it after the texture, but I don't think it matters. Okay, let's just do it here. So we're going to create a GLM mat4, call it model, and it's going to be equal to GLM mat4 1. All right, model equals glm rotate. Okay, how much is it rotating? Minus 55. And finally, glm, what's this, select 3. Did not mean to do that. Right, so this will be on the x-axis, so 1.0, 0.0, 0.0. this is not going to do anything. I just want to stop this from rotating for now. That is the transformation matrix, and this is where we're transforming it. And this is a translation. So it should be centered now. Yep. All right, now we're going to use this model matrix. By multiplying the vertex coordinates with this model matrix, we're transforming the vertex coordinates to word coordinates. Our plane that is slightly on the floor thus represents the plane. To move the camera backwards. Okay, next we need to create a view matrix. We want to move slightly backwards in the scene so the object becomes visible. When in world space, we're located at the origin 000 to move around its scene. Think about the following. To move the camera backwards is the same as moving the entire scene forwards. That is exactly what a view matrix does. We move the entire scene around inwards to where we want the camera to move. Because we want to move backwards, and since OpenGL is a right-handed system, we have to move in the positive z-axis. We do this by translating the scene towards the negative z-axis. This gives the impression that we are moving backwards. Okay. Okay, so it's just showing what the right-handed coordinate system is. Z-axis forward is negative z, back is positive z, right is positive x, left is negative x, up is positive y, and down is negative y. Okay, that's fine. We'll discuss how to move around the scene in more detail in the next chapter. For now, the view matrix looks like this. All right, might as well add the view matrix. So we have GLM mat4 view, and we can initialize that with GLM mat4 .0. Okay, note that we're translating the scene in the reverse direction of where we want to move. So here it is doing a GLM view equals GLM translate. Then it's going to translate the view with GLM vec3, and it's going to be 0 0 minus 3. Okay, so minus 3, we're translating the scene in the reverse direction we want to move. So we want to go back. We want to take the camera back. That means that's the same as taking the whole scene forward. And to go forward, you just move it in the negative z direction. So that's why this is minus 3. The last thing we need to define is the projection matrix. We want to use perspective projection for our scene. So we'll declare the projection matrix like this. We're gonna make a mat4 called projection. Okay, that's kind of odd. Why didn't it initialize it like this? Okay, we'll keep that in mind. Projection equals GLM perspective. GLM radians 45. Yep. and then the aspect ratio, which in this case is 800. Wait, should I just make a const for this? Yeah, I guess I'll just do that. HEIGHT. You're just gonna make sure it still works. Yep. Okay, gonna use the same window width and window height here. And finally the near and the far plane. Cool. Is this not correct? Okay, I think this needs to be converted to float. Okay, seems right. Now that we created the transformation matrices, we should pass them to our shader. First, let's declare the transformation matrices as uniforms in the vertex shader and multiply them with the vertex coordinates. Okay, so here we're gonna get all the matrices, the model, the view, and the projection inside our shader, the vertex shader. Okay, it's gotten rid of everything else. It's fine, I can keep those. So that's that. And then it's gonna multiply it with this. Note that we read the multiplication from right to left. So yeah, first we do the model, then the view, and then the projection from right to left. So we'll do it like this. Like for a pos is this part, we're not transforming it anymore. So first multiply it with the model, then with the view, finally with the projection. Okay, are they set to something? Yeah, they need to be set already first. We should also send the matrices to the shader. This is usually done each frame since transformation matrices tend to change a lot. Okay, int model location is equal to get uniform location, the model, and then we set it to this. Now that our vertex coordinates are transformed where the model, view, and projection matrices, the final object should be like this. Okay, that's interesting. So I'm going to set the coordinates. Okay, when I'm doing the uniform, I'm setting the uniform. Okay, I think I can do it inside the render loop. I don't actually need to send this anymore. It's fine. Model lock. Will GL get uniform location? Need to pass it the shader ID and the name of the uniform. And then to set it, we do GL uniform matrix 4 FP. Okay, understand GL matrix 4, uniform matrix. F, I suppose, means float. What does V stand for? Okay, I guess I'll have to look that up later. Model lock. So that will be the location. Setting 1. What is this? Anyway, GL false. GLM value pointer model. Oh yeah, it needs to convert it. I remember now. And we pass it the data. Yeah, that's how you set the model, view, the projection. All right, and that should add perspective. Awesome. Okay, so it's doing that. Now that our vertex coordinates are transformed, it's tilted backwards to the floor a bit farther away from us. Yep. Be displayed with the perspective. It should get smaller the further away the vertex are. So we have all three of those things. Let's check if the result actually does fulfill the requirement. It does indeed look like the plane is a 3D plane that's resting at some imaginary floor. If you're not getting the same result, compare your code with the complete source. So far we've been working with a 2D plane even in 3D space. So let's take the adventurous route and extend our 2D plane to a 3D cube. To render a cube, we need a total of 36 vertices, 6 faces times 2 triangles times 3 vertices each. 36 vertices are a lot to sum up, so you can retrieve them from here. For fun, we'll let the cube rotate over time. Okay, so this monster is going to be our vertices. Vertices array right here somewhere. Okay, I'm just gonna comment this out for now. Wait, 1 2 3 4 and 5. This has 1 2 3 4 5 6 7 and 8. So is this for the texture coordinates or is this the color? I don't think it's the color though. Okay, we'll see. So that'll be our vertices. It's gonna look weird. Yep. Okay, so and then we'll draw the cube using GL draw arrays. We didn't specify indices, but this time with a count of 36. So rather than doing GL draw elements, we're just going to do the shortcut method of doing GL draw arrays, GL triangles, start from 0 and go up to 36. What will that do? Yep, still looks like a mangled mess. If you get something like this. Okay, I think because it's expecting color attribute, but we're not passing color attribute. So maybe should we just, well, we're not using it. 3, 3 and 2. Okay, this seems fine. 8. It's not 8 anymore, is it? 1, 2, 3, 4, 5, 6, 7, 8, and here it's just 1, 2, 3, 4, 5. I think this is the stride, so it's just going to be 5. And then it starts from the beginning. This is going to start from, okay, it started from 6 here. 1, 2, 3, 4, 5, 6. There's 0, 1, 2, 3, 4, 5, 6. Now it has to start from 0, 1, 2, 3. So this is 3. Hopefully this will work. Alright, that worked. Okay, so you should get something similar to this. It's not rotating. Okay, for that we're going to use the model matrix, which is the converts it from local to global space. So for that, it's just going to rotate it. Oops. Okay, here we're going to rotate it here before passing the uniform. Okay, this code is a mess. I'm going to clean it up after this. Just get rid of all the previous stuff. Okay, model equals rotate. Yep, glm rotate, and we're going to rotate the model by, okay, we're going to need to cast it to float, and we're going to rotate it by glfw time get time. And times it by radians 50. Okay, and we're going to be rotating it on this. Is this the axis? Yeah, it should be the axis. glm vec 3 0.51 0.5 f 1.0 f comma 0. Okay, so that should rotate it. That's really too fast. Try doing differently. glm rotate the model, glm rotate model, and float glf get time, glw get time, times glw radians, glm radians 50. Yeah, I don't know why it's going so slowly for you. I guess I can just tell it to go slower like this. Yep, okay, it's still too fast. I wonder why that is. And then we'll draw the cubes, we'll GL try raise. Why is it so? Use the vertices. This seems to be the speed that's rotating here. Okay, it's actually rotating even slower than this for some reason. Anyway, it does resemble a cube slightly, but something's off. Some sides of the cube are being drawn over at the sides of the cube. This happens because when OpenGL draws your cube triangle by triangle, fragment by fragment, it will overwrite any pixel color that may have been drawn over there or before. Since OpenGL gives no guarantee on the order of triangles rendered within the same draw call, some triangles are drawn on top of each other, even though one should clearly be in the front. in front of the other. Luckily, OpenGL stores depth information in a depth buffer called zbuffer that allows OpenGL to decide when to draw over a pixel and when not to. Using the zbuffer, we can configure OpenGL to do depth testing. OpenGL stores all its depth information in a zbuffer, also known as depth buffer. GL will automatically create such a buffer for you, just like it has a color buffer. It stores the colors of the output image. The depth is stored within each fragment as the fragment's Z value. And whenever the fragment wants to output its color, OpenGL compares its depth value with the Z buffer. If the current fragment is behind the other fragment, it is discarded, otherwise overwritten. This process is called depth testing and is done automatically by OpenGL. However, if we want to make sure OpenGL actually performs the depth testing, we first need to tell OpenGL we want to enable depth testing. It is disabled by default. We can enable depth testing using GL enable. The GL enable and GL disable functions allow us to enable disable certain functionality in OpenGL. That functionality is an enable disable until another call is made to enable disable. Right now we want to enable depth testing by enabling GL depth test. Okay, just do GL enable GL depth test. I guess we can just do it at the top. Is that it? Nope. Since we're using the depth buffer, we also want to clear the depth buffer before each render iteration. Otherwise, the depth information of the previous frame stays in the buffer. Just like clearing the color buffer, we can clear the depth buffer by specifying the depth buffer bit in the GL clear function. Okay, so on every render loop, we were doing the GL clear somewhere here. Okay, this thing right here. So here we're just doing the color buffer bit. We can, or with this, the GL depth buffer bit, is that what it's called? Yep, depth buffer bit. Okay, and that should clear the buffer, the depth buffer on each frame. Great. Okay, so that's awesome. Let's rerun our program and see if GL now performs depth testing. There we go, a fully textured cube with proper depth testing that rotates over time. Say we want to display 10 of our cubes on screen. Each cube will look the same but will only differ in where it's located in the world, with each a different rotation. The graphical layout of the cube is already defined, so we don't have to change our buffers or attribute arrays when rendering more objects. The only thing we have to change for each object is its model matrix, where we transform the cube into the world. First, let's define a translation vector for each cube that specifies its position in world space. We define 10 cube positions. Okay, so it's a vec3 array, and each of these defines the cube's position. Let's do that up here. Now within the render loop, we want to call GLDrawArrays 10 times. For this time, send a different model matrix to the vertex shader. Each time before we send out the draw call, we will create a small loop within the render loop that renders our 10 objects. That renders our objects 10 times with a different model matrix each time. Note that we also add a small unique rotation to each container. Okay, GL bind, it's doing that here. This is all the matrices. And then rather than doing the GL draw arrays here, it's gonna do a loop, create the model matrix, set it to the cube position that we defined, change the angle, rotate it by that angle, and then set mat4 and send the model matrix, and then do the GL draw arrays. Okay, so I suppose that can be done here. It can be done here, but I'm already setting the model matrix here. Then I'm setting it again here, which I suppose will just be overwritten. But we can just comment that out. I don't think set mat4 is defined for me. Okay, I just have bool int and float, so I'm gonna need to do the set mat4. Where is the source code for this? Where can I get the shader? Okay, there it is. Okay, and I can add the set mat4 function. It also has other functions here. Okay, we'll add those later. Okay, that should allow this. Okay, what the hell? It needs GLM. Same as this. Okay, let's try again. Yeah. So we have our cubes. Perfect. It looks like our container found some like-minded friends. If you're stuck, see if you can compare your code with the source code. Try experimenting with the FOB and the aspect ratio parameters of GLM's projection function. See if you can figure out how these affect the perspective system. Play with the view matrix. Let's first try changing the FOB. That'll be fun. So this is what we get at 45 degrees. If we have something like, let's see, let's try 90. Hey, everything looks smaller. Okay, so that's that. And the aspect ratio, let's try doing 300 rather than 600. Okay, so it actually squishes it. And if we do it here, it will, I guess, squish it on the y-axis. Yep. Okay, cool. So that's why we need to know what the aspect ratio of the screen is. Play with the view matrix by translating in several directions and see how the scene changes. Think of the view matrix as a camera object. So this is our view matrix. Here we were just translating it by translating it on the z-axis a little bit. But I guess if we want to take it up, we would take the entire world down. So let's try -3 on the y-axis. Yeah, so it's like taking the camera up. Cool. I guess we can also try rotating this. I don't know if what the correct order for that would be. Okay, say I want to rotate it downwards. That would be the x-axis, and let's say I want to rotate it by 30 degrees. Maybe it should be minus 30. Right, so it is actually like looking down. Okay. Let's try the other one. I'm not sure. Okay. What exactly is it doing? Let's actually try not to translate it for now. Okay, so it did like move down a little bit. Yeah, so this is like the camera is looking down. Alright, the stream has been going on for like 58 minutes. I think this is a good enough result, so we can stop here. Next week, I guess, is going to be the most fascinating chapter, at least in my opinion. I'm really looking forward to that. We're going to be creating the camera. Cool. All right. If you want to watch this and all the previous videos, you can actually go to YouTube on twitch.tv. You'll just find the link for this. See right here, or you can just click on the YouTube channel, and this will take you to my YouTube channel. You can find all the previous days here, and I'll just be uploading this day 6 as well, and you can follow along. All right, so that was day 6, coordinate systems of learning OpenGL. See you, bye bye.